Welcome to Statistics, Unit 3, Lesson 5. How good are the predictions for Barbie? Today we're going to talk about the least squared regression line as a prediction line. It is a prediction line, and that's exactly what its function is, but we're going to talk about what it predicts. All right, please go ahead and open up to your lesson. How good are the predictions using Barbie data? Okay, so this is the data that I'm going to have you use. And I'm going to have you go ahead and put this into your calculator. The one data I don't want you to put in your calculator is 5, because you can see it has a question mark. It's missing. So we're going to put it into our calculator. So let's go ahead and open up a new spreadsheet. And I'm going to just put in here. I'm going to put A just so it'll come up to the top of mine. A rubber band. And that's 0, 1, 2, 3, 4. I'm skipping 5, 6, and 7 because I don't have the data for 5, and that's intentional. Okay, and I'm just going to go put A distance just so it shows up. I have so many, and I want it to show up for me on the first thing on my calculator. So this is 25, 32, 41, 49, 55, 69, and 78. Okay, so we're going to add data statistics. This is going to be a rubber band, and this is going to be a distance. Let's go ahead and make a regression line. Menu, analyze, regression, show linear, the second one. And this is my regression line. If I go back to it, I can go ahead and do my menu, stats, test, and go down to A, which is linear regression. And this is going to be a rubber band and a distance. And now I have all my data ready to go. Okay, so the first thing asked me is go ahead and write my prediction line. So my prediction line you can either get from here where it's A plus BX, and you would put 25.33 plus 7.46, and my X is my number of rubber bands. Now notice I have it written in the red, and that's the way I want you to write it. Notice there's a hat over the distance, and that hat means that it's a prediction, because the line is a prediction, and so that's what when we put the hat over, that reminds us that's what it is. And notice I don't put X and Y. I just go ahead and put distance and rubber bands. So use the regression line to predict for 5 rubber bands. So if I'm predicting for 5 rubber bands, remember my X is equal to rubber bands. You're just going to put the 5 into my equation. So this here is 62.63. And so that's my predicted distance traveled. And remember, we put a hat over the distance to remind us that that's exactly what it means. One of the group members later found a measurement for 5 rubber bands, and they said, oh, wait a minute, it's actually 64. So I'd go back up here, and I could put this in here and say, this I know is 64. We predicted it to be 62.63. And obviously, our prediction's too low. And so my actual minus my predicted, that's considered my residual. And so I missed it by 1.37. That's what my residual does, is tells me how much I miss it by. The acronym I try to remember for residual is RAP. Residual equals actual minus predicted. Actual minus predicted. Okay? So the prediction of the distance traveled for 20 rubber bands, we're going to predict that. And would you trust this prediction? So if I put 20 in, I get 174.3, but I only have between 0 and 7. This is my domain. Do you guys remember domain and range? My domain is all my X values, is between 0 and 7. If I predict something higher than 7 rubber bands or lower than 0 rubber bands, even though that's impossible, we call that extrapolation. Extrapolation is when I'm trying to predict something that's outside my domain. And so therefore, it's actually unreliable. So the y-intercept, that was just this here. And I know that's easy for you guys to see because that's from like algebra. It's just the one that's without the x. But to interpret it, just make sure you interpret it correctly. Meaning, that means just when I have no rubber bands or the starting height. And you have to use the word predicted. My predicted distance that the Barbie's going to have traveled is 25.33 centimeters. And that's basically Barbie's predicted height, how tall she is. Because, and remember, when we did it, it was how tall she was at her lowest hanging point, like her hair or hands or whatever was lowest. Secondly, slope. We're going to do the slope, and remember the slope is just the one that was next to the y, or next to the x, and that's 7.46. And you just need to describe it though. For every 1 rubber band, we predict it to increase by 7.46 centimeters. So, with our regression lines, the learning target number 1 is making predictions. To make predictions, you're just going to plug in your value to my x, and then you're going to solve. But be careful of extrapolation. If it's outside my domain, you cannot, and it is not reliable. We're not necessarily saying it's wrong. We're just saying it's not reliable. It's kind of like a growth chart. When you were a baby, you grew a lot. Like, imagine a baby here, newborn, and let's say you're about, 6 pounds as a baby newborn. And then at 1 year, let's say that now you're about 24 pounds. So you have multiplied by 4 your weight. Then let's say, if we use that thought, then 6 times 4 is 24 pounds. Times 4 is at year 2. If we keep with this, it's 96 pounds. And then again, year 3, you're at 384 pounds. And at year 4, you're at 1,536 pounds, which you can see is absolutely ridiculous to be able to keep getting that heavy. The problem is that babies obviously grow a ton between 0 and 12 months. And then, they grow really a lot, and then they start to slow down. And then they start to grow again. They get another growth spurt in their teenage years, and then they slow down. And then they don't grow at all in height, just in weight when they become a full adult. Residual is my actual minus predicted. Let me draw for you what a residual is. Okay? This line is my regression line, the predicted line, the kind of what we did over here when we looked at here, when I graphed it, right? That's my prediction line. And these here are all the dots that are on my line, or that we got the line from. The distance here, so this is my actual. And then the line itself is my prediction. Let's kind of zoom it in a little bit. So this distance here, the actual minus the predicted, that's called my residual. Kind of what we did over here, where this one here, when we had was 5, so we had 5. We predicted that was 62.63, but his actual was 64. So the picture would look like this. So this distance here is 1.37, and we say that's the residual because that's the actual data minus the predicted data. My slope is my predicted change in y. That delta means change in y for the increase. And remember, the line, just the plain constant, the plain number is my y-intercept, and that's predicted when x equals 0. And this here, the slope is predicted for the change in y for each x. Now, remember, this does kind of look a little weird, I'm sure, because in algebra, you're used to y equals mx plus b. So this is honestly the same thing, except in stats, we do y equals b plus ax is how we have it. Or, I'm sorry, I wrote it wrong. A plus bx is what I meant to say. So it's a little bit different. Where in stats, my slope is my b, and in algebra, it was my m. In stats, my y-intercept's my a, and in algebra, it was my b. So it's a little bit different. Okay, so calculate and interpret the residual for the flour that had 2 tablespoons of sugar and looked fresh for 204 hours. So the first thing we're going to do is we're going to put a 2 into my equation, which this is my equation, so that we can get the actual. So this is my actual. The residual is my actual minus my predicted. So this is my predicted. But it said for 2 hours. So if I look here and I look at the predicted line right here, you can see that for a tablespoon for 2 is going to be, I guess I have it off a little bit. Hold on, let me get it. I guess when you put it in, that's my actual, oh, I'm sorry. My actual was actually 204, and my predicted, this is my actual right here. There. And my predicted was right here. So the actual one is going to be 204, because that's what it told me right here. And then my predicted was putting it in. So looking at the graph, it had a couple different ones. There were 3 different values that had different vases that had 2 tablespoons of sugar, and they ended up having 2 different values. But this particular one had at 204. So that's where the actual is 204, and the predicted is 212.84 or 0.4, and that's a negative 8.4 hours. And you can see on the graph how this is my predicted, and this is my predicted, and that's my actual. So since the actual is lower than the predicted, it's going to be negative, because remember, it's residual equals actual minus predicted. Okay, now interpret the slope and the y-intercept. So just the slope is just going to be 15.8, because you can see it's right here. And that means the predicted number of hours, the freshness increased by 15.8 hours for each 1 tablespoon of sugar. The y-intercept is 180.8. If the vase receives 0 tablespoons of sugar, the predicted number of hours of freshness is going to be 180.8. It's just initial value without changing anything. Okay, would you be willing to use the regression line to change for this to predict the freshness for the flour for 10 tablespoons? And no, because my data only has between 0 and 3, so 10 is way outside that. So it might actually change the data so much, and it might not be accurate. So we cannot do that, because that is called extrapolation. Okay, thanks for listening, and I'll see you later.